Let's imagine a ship sailing through the sea. It starts its journey from a point. Let's call this point the origin. First, the ship travels 150 meters in one direction. Then it changes its direction slightly and moves 120 meters. Finally, it changes direction once more and travels another 100 meters. So, the total distance covered by the ship is 150 plus 120 plus 100 equals 370 meters. Now, here's a question. If the ship has traveled 370 meters, can we tell where the ship is right now? Not really, because distance only tells us how much path the ship has covered, not where it is from the starting point. From distance, we can calculate speed, which tells us how fast an object moves, but not in which direction. The formula for speed is speed equals distance divided by time. For example, if the ship covers 370 meters in 185 seconds, its speed equals 370 divided by 185, 2 meters per second. That means the ship moves 2 meters every second, but we still don't know its final position. To find that, we need displacement, the shortest straight-line distance from the starting point, the origin, to the ship's final position, along with the direction. Displacement tells us the ship's actual position from where it began. Now, when we consider both displacement and time, we get a new quantity called velocity. The formula for velocity is velocity equals displacement divided by time. Velocity tells us how fast and in which direction the position of an object changes. So if we know the velocity of the ship and the time it's been moving, we can find out where the ship will be after that time. That's why velocity is more meaningful than speed. It not only tells us how fast something moves, but also helps us determine its position and direction. Velocity depends on two things: how fast an object moves and the direction in which it moves. To understand how velocity behaves in different situations, let's look at uniform velocity and variable velocity. First, uniform velocity. Imagine a car traveling 18 kilometers in 1 hour along a straight road. If the car continues to move with the same speed and in the same direction, then its velocity remains unchanged. This is called uniform velocity. Velocity stays uniform only when both conditions remain constant. The speed does not change and the direction does not change. Now let's look at variable velocity. Consider another car moving with the same speed, but this time along a curved road. Here, the speed is constant, but the direction changes at every point of the curve. Since a change in direction means a change in velocity, this is an example of variable velocity. Velocity becomes variable in any of these situations: if the speed changes, if the direction changes, or if both speed and direction change. If any of these conditions occur, velocity cannot remain uniform. To summarize, uniform velocity occurs when an object moves with the same speed and in the same direction. Variable velocity occurs when the speed changes, or the direction changes, or when both change. Next, let's understand average velocity. Average velocity is the total displacement divided by the total time taken. It tells us how fast an object changes its position in a specific direction. For example, if an object moves 100 meters east in 20 seconds, then average velocity equals displacement divided by time, equals 100 meters divided by 20 seconds, equals 5 meters per second east. Average velocity always includes direction, because velocity is a vector quantity. Now let's explore another important idea: average velocity when the velocity of an object changes at a uniform rate. If the velocity increases or decreases by the same amount in equal intervals of time, the motion has uniform acceleration, and we can use a simple formula. Average velocity equals initial velocity plus final velocity divided by 2. This formula works only when the change in velocity is uniform. Let's look at an example. Suppose an object starts with a velocity of 10 meters per second. Its velocity increases uniformly to 20 meters per second and then to 30 meters per second. Here, the velocity is increasing uniformly. Each time it increases by 10 meters per second. Using the formula, average velocity equals initial velocity plus final velocity divided by 2 equals 10 meters per second plus 30 meters per second divided by 2 equals 40 meters per second divided by 2 equals 20 meters per second. So the average velocity during this motion is 20 meters per second. This method makes it very easy to calculate average velocity whenever the change in velocity is uniform. That brings us to the end of today's lesson. We explored some important ideas about motion and saw how understanding these basics helps us describe how objects move in the real world. Keep practicing these concepts, and you'll find motion becomes much easier to understand. Thanks for watching, and I'll see you in the next video. If you found this lesson helpful, don't forget to like the video, share it with your friends, and subscribe for more easy science explanations.